So today we're going to be looking at how we can find the final volume and the final temperature of a system given some initial and final conditions. Our system looks something like this. We have a vessel and we have some water put in it initially, liquid water, and of course some vapor will form. And we seal the system without removing any of the air. And then we heat the system to a final pressure that we know, and we need to solve for the final volume, or the volume total because it doesn't change. We need to solve for the final temperature that we heated the system to. So we know our initial pressure is 1 atmosphere, or 101,325 pascals. We know that our final temperature is, our initial temperature is 298 Kelvin. We know that the initial mass of water that's put into the system, so our total mass of water, which won't change, is 1 kilogram. And we know that the number of moles of vapor water after the system has been heated is 0.3 moles. And this can also be expressed in terms of the mass and the molar density. So we have mass of water in the vapor phase divided by the molar density of vapor water, or 10 to the negative 3 times 18 kilograms per mole. So from here we can just start writing down some equations. We have two unknowns up here, so we know that we're going to need at least two equations, but we are going to need more in this case. So we know that our total volume is of course going to be equal to the volume of the liquid plus the volume of the vapor. Fix that up a little bit. We know that our total mass is going to be equal to the mass of the water in the liquid phase plus the mass of the water in the vapor phase. We know that our total pressure is going to be equal to the partial pressures of actually we'll go ahead and write that as our final pressure. It's going to be equal to the partial pressures of our water and our partial pressure of air. And if you remember the Antoine equation we did in an earlier video, we know that log base 10 of pressure, in this case it's going to be the pressure of the water, is equal to A minus B over C plus T. And then if we raise everything to the, or raise 10 to the everything, or 10 to the either side, we know that the pressure of water is equal to 10 to the A minus B over C plus T. So I should clarify that this is final temperature. Forgot the F there. And we already know what our partial pressure of water is. We have that over here. So we still need to find out what our partial pressure of air is. So we can assume air is acting as an ideal gas. So we know that pressure times volume equals number of moles times R times the temperature. So to isolate our pressure of air, all we have to do is divide both sides by the volume. So we know that pressure of air is equal to the number of moles of air times R times our temperature final divided by the volume of the vapor phase. Over here, we know that our density of water, we'll try that again. There you go. This isn't a P, this is the symbol rho for density of our water in the liquid phase is equal to the mass of the water in the liquid phase divided by the volume of water in the liquid phase. So now we can find our volume of water in the liquid phase pretty easily. We know our mass of water total, and we can find our mass of water in the vapor phase fairly easily. So we can express mass of water in the liquid phase as mass of water total minus mass of water in the vapor phase divided by our density of water in the liquid phase. So now we're good there. We can express the volume total in one known and so far one unknown. We know that our mass of water total and our mass of water vapor up here. We have our partial pressure of water, and we still need to find our partial pressure of air. We can't find it yet because we don't know the number of moles in the air. So I'm going to go ahead and give us a little bit more room. So we know that our number of moles in the air can be expressed as the partial pressure of air initial times the volume of the vapor phase all over R times temperature initial. And we can go ahead and expand these two terms. So we know that the pressure of the air initially can be expressed as the initial pressure minus the pressure of the water. And we know that the volume of the vapor phase can be expressed as the volume of the water total minus the volume of the liquid, which we have right here, all over R times the initial temperature. And we can go ahead and write down one more equation. We know that 0.3 is equal to our number of moles of water in the vapor phase at our final temperature, which can also be expressed as the pressure of water at our final temperature times the volume of the vapor phase all over R times our final temperature. And from there, we have enough to solve this equation. So now that we have all the equations that we need to solve for our total volume and our final temperature, we can go ahead and start coding it up in Python. The first thing we're going to do is we're going to clone a GitHub repository to our Python environment here. This is the repository that we're going to be cloning. It has some data for different substances and then some tools that we're going to be using. So we can go ahead and copy this clone link here. And all this is going to do, again, is clone it over to our environment here. And then we can actually specify that we only want the most recent version, which is what this depth1 does. If we go ahead and run that, it's probably going to give me an error, and that is because I have previously imported it here. So as you can see, we have everything that we need, all our data, and all our tools. So I'm going to actually go ahead and comment that out because I don't like seeing errors on my code. And then from there, we can import system, and all this is going to let us do is specify the file path that we want our Python to look for tools that we're going to be using. And we want the file path that we specify to be the first place it looks. And then our file path is over here, /content/che tools. So I'll just copy the path because I'm lazy. And if we go ahead and run that, oh, not very bright here. Import system and then system path insert. There we go. So now we are almost ready to start using these tools. So from here, we're going to import our tools.che as che. And then we're also going to import a function from SciPy. So from SciPy.optimize, we're going to import the root function. And then we can also specify our R value that we're going to be using. No errors there, so that's good. And then our R value is going to be 8.314. And then we can't really specify the units in the code, but we can go ahead and comment. That's in joules per moles times Kelvin. So from here, we can set P is equal to che.props. Props is a class of an object, and we are going to instantiate water. And all this means is that we're specifying we want to work with the functions and formulas associated with water. Go ahead and check that. Looks good. So here we can start setting some of our knowns. if we take a look at our notes here, I actually added the final pressure here. It's 200,000 pascals. Sorry it looks rough. I did it with a mouse. So our final pressure that we want to get to is 200,000. We know that our initial pressure is 101,325 pascals, and our initial temperature is 298 Kelvin. So we can go ahead and say pressure initial equals 101,325, and our temperature initial is equal to 298 Kelvin. We could write the units with these, but I'm going to go ahead and skip that for now, just assuming we're using standard SI units for everything. So we also know that our total mass of water is 1 kilogram. And then we know that the number of moles of water that we desire in the vapor phase is 0.3. So from there, we can go ahead and create a system of equations. So we'll define equations, and then we want our input to be a vector. And then this vector is going to be the two values that we're trying to solve for, so volume total and the final temperature. So this is just unpacking again, and it just means that we're saying these two values are going to be the two values in the input vector v. And we can start putting in some of our equations. So we can go ahead and keep putting in some of our equations. We know the pressure of the water is going to be equal to the vapor pressure at our final temperature. We also know that we can express the number of moles of air as the expanded function that we did earlier. So we can say the initial pressure minus the pressure of water at the initial temperature, so we can express that as the vapor pressure at time or temperature initial. And then that whole term can be multiplied by the volume of vapor. So remember, we expanded that. Accidentally turned on caps lock here. We expanded that to be volume total minus the volume of the liquid, and we can further expand the volume of the liquid to be the mass total. Let's double check how I put that in above. Okay, so that's good. And then divided by the density of liquid water at the initial temperature. So to get that, say pi or p dot rho L, and initial temperature. So the next thing that we can put in is the mass of water in the liquid phase is going to be equal to the total mass of water minus the mass of water in the vapor phase. And if you remember, we can find the mass of water in the vapor phase by simply multiplying the number of moles we have of vapor water with the molar density of the water. So it will be mass of the water total. Let me double check that I have it the same as we do above. So we have mass of water total minus our desired number of moles of water times the molar density, which is 18 times 10 to the negative third. Then we can also say that our volume of liquid water is equal to our mass of liquid, and I see I have a typo up here, is equal to our mass of liquid water divided by our density of water at our final temperature. So we have p dot rho L at our final temperature. The final equation that we can put in is the pressure of air is equal to the number of moles of air times R times our final temperature, all divided by the volume of the vapor. And we can go ahead and set what our function here is going to return. So we want it to return the difference between the pressure that we get from this and then the pressure we desire, and same for the number of moles of water vapor, because we're trying to minimize this, and the closer we can get to zero, the more accurate the computer can find the roots of the volume total and the temperature final. So we want it to be the pressure final that we get from using these equations minus the pressure that we desire, and then same thing with the number of moles of vapor. Okay, and then from there, all we have to do is use the root function that we imported earlier. And the arguments that we're going to be giving it is the function that we're going to be using, which is going to be our EQS here, which contains all of our equations. Now we have to provide it an initial guess for the input, and for us that's going to be the total volume and the final temperature. So we need to first guess what the total volume is, and for now we'll just say 1 cubic meter and 350 Kelvin. Go ahead and run that. There we go. So here is our final answers, and then I'll just take those two answers by themselves. Okay, so here's our final or our total volume, which is 0.00126 cubic meters, and then our final temperature is 366 Kelvin.